So this is the first part related to shape deformation. And in this first part, we will see briefly volume-based deformation using parametric settings for an interactive use. So parametric deformations consist in explicitly defining the transformation from a few sets of parameters. A logical way of defining such parametric deformation is to consider the generalization of an affine transformation with parameters that varies in space. Using rotation with varying angle can lead to model bending or twisting, and using scaling we can model squeezing or tapering behavior or stretching. So we can see some example in the image, noting that the local axis Z need of course to be adapted to the shape we are deforming. And this use is actually an old idea that was initially proposed by Alan Ashbar in 1984. Such representation has the advantage of having an explicit and close formulation, but the type of deformation is of course limited by the choice and complexity of this parametrization. So deformation can also be thought as a way to sculpt details on a shape, like pulling, carving, squeezing some part, typically under the gesture of the user. So this kind of sculpting tools are common in modeling software like Blender or Maya, and they are one of the primary tools used by artists to generate details. So these deformers, they are mostly implemented as simple parametric functions that are locally applied on the shape around a position that depends on the mouse or cursor's trajectory. And let us consider an example where a translation T is applied only locally around the 3D point C. Then we can define the deformation as Q is equals to P plus W of P times T, where W of P is a local weight that expresses how much translation is applied to a position P. To get a smooth deformation in space, we can choose W of P to be defined, for instance, by a Gaussian of the distance between the vertex position P and the center of application C. And of course, the translation T can be controlled interactively by the gesture of the user. This works for translation, but it can be generalized to other deformation with different control, such as rotation with different axes and angle, and so on. And now is some questions to prepare the actual work of the lab class where you will implement such local deformer. So in this example, we have a local translation. The user can select a position of the surface at coordinate C. The radius of the local deformation is parameterized by a radius R that you can visualize with the red circle. And the user uses a drag and drop system to pull and translate the piece of surface. As the drag and drop is done with the mouse, you have actually as input a 2D translation vector corresponding to the displacement of the mouse expressed on the screen coordinate system, which means that X and Y coordinate are between -1 and 1. Now the question is, how can we compute the deformation to apply to the shape? And we can start by loop over all the vertex coordinate P, and then you have to complete this algorithm. And now this is a slightly different example. Try to look carefully at what can be the difference with the previous case, and what should you modify in the formulation to achieve this result. In this third case, we have some local scaling and rotation. And so similarly, try to find how you can parameterize the deformation to get these results. And as a last point, we presented the case where we applied the deformation to vertex position. So when we deal with explicit representation of surface. But in some cases, we may represent shapes as implicit surfaces, which are the ISO value of a scalar field. Let's suppose that this scalar field is described as J, and the surface to be the zero isosurface of J. And we want to apply the volume deformation F, which associates a position P to F of P. Actually, the implicit surface S prime deformed by F is given by the composition G of F inverse of P. So you need to beware of that. To apply a deformation to an implicit surface, you actually need to apply the inverse transform of the deformation to the spatial coordinate as input, and then evaluate the function J to this coordinate. So the logic is the following actually. A position P belongs to the deformed isosurface if its pre-image is on the undeformed isosurface. And its pre-image is F inverse of P. And it has to be such that J of F inverse of P is equals to 0.